Before the tank rolled across European battlefields, before massive bulldozers carved highways through mountains, before tracked vehicles became synonymous with unstoppable mechanical power, there was a California farmer's nightmare and one man's audacious answer. In 1904, Benjamin Holt watched a 50-ton steam tractor sink axle-deep into the peat soils of the San Joaquin Valley, its massive wheels spinning uselessly in the mud like a dying mammoth. What emerged from his workshop would change warfare, agriculture, and construction forever. A 20-ton behemoth that didn't roll on wheels but crawled on metal tracks, distributing its weight across 15 feet of articulated steel. This is the story of the Holt Steam Crawler Tractor, the machine that taught vehicles to walk on impossible ground, the grandfather of every tracked vehicle from bulldozers to moon rovers, and the iron dream that turned swampland into farmland and inspired the weapons that would reshape the 20th century. Here's something they don't tell you about the early 1900s. The most advanced farm machinery of the era was also its greatest liability. A typical steam traction engine could weigh 50,000 pounds fully loaded, generating tremendous power through boilers running at 150 pounds of pressure per square inch, enough force to pull a dozen gang plows through virgin soil. But concentrate that weight onto 4 wheels, each supporting over 12,000 pounds, and you had a recipe for disaster. In the reclaimed wetlands of California's Central Valley, where irrigation had transformed ancient lake beds into potentially fertile cropland, these iron giants would sink 18 inches into the earth within minutes, their steel wheels cutting trenches rather than finding purchase. Farmers watched helplessly as $5,000 machines, the equivalent of $150,000 today, became expensive anchors, requiring teams of horses and days of labor to extract. Benjamin Holt understood this problem intimately. As co-owner of Holt Manufacturing Company in Stockton, California, he'd built his fortune selling combine harvesters and steam tractors to the booming agricultural industry. But he'd also witnessed the heartbreaking spectacle of his own products failing in the very conditions they were meant to conquer. The delta peat soils, rich in nutrients but soft as pudding when wet, would swallow conventional machinery. Some farmers laid wooden planks ahead of their tractors, creating temporary roadways that crews would then retrieve and reposition, a Sisyphean task that turned plowing into an exercise in futility. The physics were brutally simple. Pressure equals force divided by area. A 50,000-pound tractor on wheels with a total contact area of perhaps 800 square inches exerted over 60 pounds per square inch on the ground, far exceeding the bearing capacity of saturated peat. Holt needed to spread that weight across a vastly larger surface area, but wheels had fundamental limitations. Make them wider and they became unwieldy and weak. Add more wheels and the steering system became impossibly complex. The answer, when it came to him, was radical. Eliminate the distinction between wheels and roadway. Create a machine that laid its own track as it moved, then picked it up behind itself and laid it again ahead, an endless road rolling beneath the tractor. This wasn't entirely original thinking. Experimenters in England and Russia had toyed with tracked vehicles since the 1770s, but none had produced a practical working machine. The challenges were immense. Designing flexible yet durable track systems, managing the mechanical complexity of drive wheels and idlers, and building something robust enough to withstand agricultural abuse while remaining manufacturable at scale. Most importantly, no one had successfully married the concept to the proven power source of the era, the steam engine. Holt would need to integrate cutting-edge metallurgy, precision engineering, and steam technology into a single cohesive machine. He would need to invent the modern crawler tractor. Imagine this: Stockton, California in 1903. A boomtown where the scent of grease and coal smoke mingles with the sweet rot of delta marshland. Benjamin Holt's manufacturing complex sprawls across several acres near the waterfront, a cathedral of industrial ambition where the clang of hammers on steel creates a constant metallic thunder. Inside the experimental shop, a dozen machinists and engineers huddle around sketches that look like mechanical centipedes, their cylindrical bodies bristling with boiler tubes, their underbellies armored with articulated metal plates. The steam tractor had evolved considerably since its crude beginnings. Holt's standard model featured a horizontal fire tube boiler, typically 8 feet long and 3 feet in diameter, where water surrounded 60 to 80 steel tubes through which hot gases from the firebox passed. A skilled fireman could maintain 150 psi, feeding the boiler a steady diet of straw, wood, or coal while monitoring water levels with an obsessive vigilance. Let the crown sheet expose itself, and you'd have an explosion that could scatter iron fragments across 100 yards. This superheated steam drove a 2-cylinder engine, usually 10 or 12 inches in bore with a 12-inch stroke, generating anywhere from 40 to 75 horsepower depending on the model. Power transmission was an intricate dance of gears and chains. The engine's crankshaft connected to a countershaft through a massive gear reduction, typically 6.1, transforming the engine's high-speed rotation into the slow, grinding torque needed for field work. From there, roller chains, each link forged from heat-treated steel, carried power to the rear axle. A competent engineer could regulate speed through throttle control and a manual clutch, though the response time measured in seconds rather than the instantaneous feedback modern operators expect. Steering required a separate mechanism, a chain and gear system that operated a differential, allowing one rear wheel to rotate faster than the other. On flat, firm ground, it worked adequately. In mud, it was a cruel joke. Holt's team began their track experiments by studying the natural world, specifically the way camels distributed their weight across broad, flat feet in desert sand. They needed to create a foot for their machine that was 15 feet long and several feet wide, flexible enough to conform to uneven ground, yet rigid enough to support 10 tons without buckling. The solution they devised was revolutionary in its mechanical elegance. Individual metal plates, each about 2 feet wide and 8 inches deep, connected by steel pins to form an endless articulated belt. These plates featured raised cleats for traction, and each weighed approximately 15 pounds. Multiply that by the 100 or so plates needed for a complete track system, and you're adding 1,500 pounds of steel just for the track system alone. The track wrapped around a series of wheels and rollers, each serving a specific function. At the rear, the drive wheel, a massive toothed sprocket 5 feet in diameter, engaged with openings in the track plates, pulling the track around its circuit. At the front, an idler wheel, slightly smaller and mounted on adjustable arms, maintained tension and allowed the track to rise over obstacles. Between these sat the bogie wheels, smaller rollers mounted on a frame that distributed the tractor's weight along the track's length. This arrangement created a footprint approximately 15 feet long and 4 feet wide, about 720 square inches per track. With 2 tracks supporting a 20-ton machine, the ground pressure dropped to around 14 pounds per square inch, less than a quarter of what a wheeled tractor exerted. November 24, 1904. The date lives in industrial history like a birth certificate for a new species of machine. In a yard behind Holt's factory, mechanics made final adjustments to a tractor that looked like something from a fever dream, a conventional steam engine perched atop what appeared to be metal railway tracks bent into continuous loops. The machine measured 18 feet from front to back, stood 9 feet tall at the smokestack, and radiated the kind of crude mechanical menace that makes witnesses step backward instinctively. Company photographer Charles Clements positioned his large format camera on its tripod, preparing to document either triumph or expensive failure. Benjamin Holt, now 56 years old and already a wealthy man, didn't need to be present for this test. He could have sent engineers, foremen, subordinates, anyone but himself. Instead, he climbed onto the operator's platform, a metal deck behind the boiler where handles, levers, and gauge dials bristled like the controls of a locomotive. The fireman, whose name history has unfortunately lost, shoveled coal into the firebox, building pressure while Holt familiarized himself with the modified control system. Where a wheeled tractor had a steering wheel connected to the front axle, this machine featured two levers that controlled clutches for each track independently. Pull the left lever, and the left track would disengage, allowing the right track to pivot the machine. It was unintuitive, requiring operators to think in terms of differential power rather than directional pointing. Steam pressure climbed. 100 psi, 120, 140. The safety valve chattered nervously at 150, venting excess pressure in white jets that caught the morning sunlight. Holt opened the throttle, and the two-cylinder engine began its characteristic double-beat rhythm, chuff, 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 driving the countershaft, which drove the chains, which drove the drive sprockets. For a moment, nothing happened. 20 tons of iron and steel resisted movement with the stubbornness of geology itself. Then, almost imperceptibly, the tracks began to move. The sound was unlike anything anyone present had heard, a continuous metallic rattling as each track plate engaged with the drive sprocket, rolled under the machine's weight, and then lifted away from the ground to begin its journey back to the front. The cleats bit into the packed earth of the test yard, and the entire machine lurched forward at a walking pace, perhaps 2 miles per hour. Witnesses later reported that it didn't seem to roll so much as flow across the ground, each track conforming to minor irregularities with an almost biological flexibility. Holt steered the machine in a wide circle, demonstrating how differential track speeds could pivot the mass without the need for a steerable front axle. The turn radius was surprisingly tight, about 20 feet, half what a comparable wheeled tractor could manage. Clement's photograph captured the moment for posterity. The machine in profile, tracks clearly visible, a small plume of smoke rising from the stack. Company Secretary R.C. Baker, watching from a safe distance, reportedly exclaimed, "It crawls just like a caterpillar." The name stuck. Within weeks, Holt would file trademark papers for Caterpillar, a name that would become synonymous with tracked vehicles and eventually one of the world's most recognized brands. But in that moment, the focus was purely practical. They'd built a machine that could potentially work ground that defeated conventional equipment. The initial test lasted 30 minutes, covering perhaps a mile of ground at varying speeds. The machine performed flawlessly. No track breaks, no derailments, no mechanical failures. Holt shut down the engine, stepped off the platform, and walked around his creation, examining wear patterns on the track plates, checking the bogie assemblies for stress fractures, running his hands along the drive sprocket teeth. The real test would come in the delta fields where wheeled tractors had failed, but for now, the proof of concept was undeniable. They'd created something genuinely new, a vehicle that conquered soft ground not through brute force, but through elegant distribution of weight across space. The San Joaquin River Delta presented challenges that made the test yard look like a ballroom floor. Formed over millennia from sediment deposits and periodic flooding, the delta consisted of islands and tracts protected by levees, with soil that ranged from heavy clay to nearly pure peat, decomposed plant matter that could be 15 feet deep in places. When dry, this peat was fantastically fertile, capable of producing wheat yields that astonished agricultural experts. When wet, it became a trap that could swallow a horse to its chest and hold a wagon wheel immobile with a grip stronger than concrete. In early 1905, Holt arranged for his crawler to demonstrate its capabilities on the Roberts Island property, 4,000 acres of reclaimed marshland where conventional tractors had proven utterly useless during wet seasons. The machine arrived by barge, offloaded via temporary ramps onto ground that visibly rippled with each footstep like gelatin. A crowd gathered, farmers, agricultural reporters, competitors, skeptics, all betting internally on whether this strange contraption would vindicate or humiliate its inventor. The demonstration began simply. crossing 200 yards of saturated peat that had defeated a wheeled steam tractor just days earlier. The crawler moved forward at its characteristic walking pace, tracks churning through the soft surface layer and finding purchase in the denser material beneath. Where wheeled tractors had sunk to their axles in minutes, leaving furrows 18 inches deep, the crawler's tracks left impressions only 4 to 6 inches deep, significant but not debilitating. The machine crossed the test section in about 10 minutes, turned around, and crossed back, demonstrating that it could work in conditions that were simply impossible for wheeled equipment. But mobility was only part of the equation. A tractor existed to pull implements, and the real question was whether the crawler could develop sufficient drawbar pull to justify its considerable expense and complexity. Holt's team hitched the crawler to a gang of 6 plows, each with a 14-inch mold board, a load that would tax any tractor. The operator opened the throttle, and the engine's rhythm deepened as load came on the system. Steam pressure dropped slightly as the cylinders drew more heavily on the boiler's capacity, but the firemen compensated, feeding the fire and maintaining working pressure. The tracks dug in, cleats gripping the soft earth, and slowly, inexorably, the plow gang began to move. The sight was transformative. Where horses would have struggled and wheeled tractors would have spun uselessly or sunk, this machine simply walked forward, dragging 6 plowshares through virgin delta soil. The furrows weren't perfect. Speed varied between 0.5 and 1 mile per hour depending on soil consistency, but the work was getting done. Calculations made later suggested the crawler was developing approximately 8,000 pounds of drawbar pull, roughly equivalent to a team of 20 horses, but with the crucial advantage of being able to operate in conditions where horses would be useless or inhumane to employ. The demonstration lasted 3 hours, plowing approximately 15 acres and consuming about 200 pounds of coal and 500 gallons of water, the latter supplied by a horse-drawn tank wagon that followed the tractor like a mechanical calf following its mother. By the end, even the skeptics were convinced. Here was a machine that fundamentally changed what was possible in agricultural engineering. The crawler could work wet ground during the critical spring planting window when every day mattered. It could access fields that had been considered too marginal for cultivation. It could transform the economics of delta farming by allowing single machines to do work that would otherwise require massive animal teams and their associated costs of feed, care, and management. The crawler solved one problem brilliantly and created a dozen others with equal enthusiasm. Within the first year of commercial production, Holt's company encountered the harsh reality that making one experimental machine work and manufacturing dozens of reliable, durable tractors were entirely different challenges. The track system, so elegant in concept, proved to be a maintenance nightmare in practice. Each track plate endured constant flexing as it rolled around the drive sprocket and idler wheel, subjecting the connecting pins to alternating tension and compression stresses thousands of times per hour. Metallurgy in 1905 wasn't sophisticated enough to predict fatigue failures accurately, so early operators learned through bitter experience. Pins would shear without warning, causing track breaks that could take hours to repair in the field. A track break at speed, and 2 miles per hour was speed for these machines, could be catastrophic. The broken track would whip around as the drive sprocket continued pulling on the intact section, creating a flailing steel weapon that could tear through metal panels and human flesh with equal indifference. Company records from 1906 to 1908 document at least 15 serious injuries related to track failures, though the actual number was likely higher. Industrial accident reporting in the era was inconsistent at best. Workers learned to maintain respectful distance from operating crawlers, particularly when working in difficult terrain that stressed the track system maximally. The drive sprocket teeth wore down rapidly under the constant grinding interaction with track plates, requiring replacement every 500 to 800 hours of operation, perhaps twice per growing season for machines working double shifts. Each tooth was individually cast and machined, representing several hours of skilled labor. The bogie wheels, supporting thousands of pounds while rolling over uneven ground, developed flat spots that created a characteristic rumbling vibration felt throughout the machine. Bearings failed with distressing regularity, particularly those supporting the idler wheel assemblies, which had to handle not just rotational loads, but also the lateral forces generated during turning. But the steam engine itself presented the most consistent danger. Operating at 150 psi, the boiler contained energy equivalent to roughly 50 pounds of TNT. Proper water maintenance was critical. Lose too much water, and the crown sheet, the top of the firebox, would be exposed to direct flame, weakening the steel until pressure blew it apart in an explosion that typically killed the fireman instantly and severely injured anyone within 20 feet. Gauge glasses, which showed water levels, had to be cleaned daily because mineral deposits would create false readings. Safety valves required weekly inspection because they were the only automatic protection against overpressurization. A stuck safety valve combined with an inattentive fireman equaled disaster. The human cost extended beyond explosive failures and mechanical injuries. Firemen worked in conditions that would be illegal by modern standards. Temperatures on the platform regularly exceeded 110 degrees Fahrenheit, coal dust coated lungs with fine black particles, and dehydration was a constant threat during summer operations. A typical shift lasted 10 to 12 hours, during which the firemen would shovel perhaps a ton of coal while simultaneously monitoring water levels, checking steam pressure, watching for mechanical issues, and coordinating with the operator. The work attracted desperate men, immigrants, drifters, those with few alternatives. Some lasted years, building specialized skills and commanding premium wages. Others quit after a single hellish day, swearing never to go near steam machinery again. Operators fared slightly better but faced their own challenges. The control system demanded constant attention. Throttle settings had to be adjusted continuously as load varied. Track clutches required precise timing to execute smooth turns, and the machine's slow response time meant anticipating terrain changes several seconds in advance. Make a mistake, and you could bury the crawler in mud, snap a drawbar, or flip the machine on a slope, the latter being particularly deadly given the 20-ton mass and the operator's exposed position. Yet despite these dangers, men lined up for operator positions. The work paid $4 to $5 per day, double what a skilled farmhand could earn, and carried a certain prestige. You were mastering the most advanced agricultural technology in existence, controlling iron monsters that could do the work of dozens. Talk to old-timers in the San Joaquin Valley, those whose grandfathers worked the early crawlers, and you'll hear stories that blur the line between industrial employment and frontier adventure. A crawler crew wasn't just a collection of workers, it was a tight-knit unit whose survival depended on coordination, trust, and specialized skills developed over hundreds of hours in the field. The hierarchy was simple but rigid: the operator, the fireman, the tenderman, who managed water and fuel supply, and often a general laborer who handled implements, performed field repairs, and learned the trade. The operator was king, making $5 per day in an era when the average industrial wage was $1.50. He was typically 25 to 45 years old, mechanically inclined, and possessed of the peculiar combination of caution and confidence necessary to command a 20-ton machine. Good operators developed an almost supernatural sensitivity to their crawler's condition, diagnosing problems by subtle changes in engine rhythm, unusual vibrations, or the particular quality of steam exhaust. They could estimate drawbar load by throttle position and steam pressure, judge ground conditions by how the tracks settled, and execute turns with a precision that seemed impossible given the crude control system. The fireman earned $3.50 to $4 per day and worked harder physically than anyone else on the crew. His day began before dawn, building fire in the cold boiler, a process that took 45 minutes to an hour, gradually heating the metal to prevent thermal shock that could crack the crown sheet or tubes. Once working pressure was achieved, his job became an endless cycle. Shovel coal into the firebox, check water level, add water from the tender tank via the injector pump, monitor steam pressure, shovel more coal. Repeat. The best firemen developed rhythms that matched engine load, anticipating when the operator would demand more power and ensuring steam was available when needed. They also served as safety officers, responsible for preventing the boiler explosions that could kill everyone aboard. Living conditions for crawler crews ranged from Spartan to appalling. Large farming operations might provide bunkhouses, uninsulated wooden structures with communal sleeping areas, outdoor privies, and washing facilities that consisted of a pump and basin. Meals were basic: beans, salt pork, bread, coffee strong enough to dissolve horseshoes. Smaller operations or contract plowing outfits often meant sleeping under the crawler itself, using the still warm boiler for heat on cold nights, or in canvas tents pitched alongside the machine. Water for washing was a luxury. Water for drinking was carefully rationed from the tender tank or whatever local source was available. Despite these hardships, camaraderie was genuine and deep. Men who worked together on a crawler developed bonds similar to those of combat soldiers or sailors, forged in shared danger, mutual dependence, and the unique experience of operating machinery at the edge of capability. They developed private languages of signals and gestures for coordinating over the engine's roar. They shared knowledge about which fields had hidden stumps or soft spots, which foremen were reasonable and which were tyrants, where to find the best price for a decent meal in Stockton. The ethnic diversity of crawler crews reflected California's immigrant labor pool: Italian firemen, Swedish operators, Chinese tendermen, Mexican laborers, all working alongside native-born Americans in a meritocracy based purely on skill and reliability. A man who kept his boiler safe and his fire hot earned respect regardless of where he'd been born or what language he spoke at home. This workplace integration was remarkable for its era, though it should be noted that management positions remained almost exclusively the domain of white, native-born men. Skills passed informally from experienced hands to newcomers. There were no training manuals, no formal apprenticeship programs, just observation, imitation, and hard lessons learned through mistakes. A new fireman might be told once about maintaining water levels, then left to figure out the injector pump himself. Survival taught what formal instruction could not: the exact sound a bearing made before failure, the subtle change in exhaust color that indicated incomplete coal combustion, the feel of track tension that meant a pin was about to shear. Those who learned survived and prospered. Those who didn't found other work, assuming they survived their education. The original crawler of 1904 was primitive by standards just 5 years later. Holt's engineers, armed with field data from hundreds of operating machines and thousands of hours of use, began a rapid evolution that transformed the crawler from experimental oddity to refined agricultural tool. The 1908 model, designated the Holt 60, represented the culmination of this early development period and established design patterns that would persist for decades. The most significant change was abandoning side-mounted drive wheels for rear-mounted drive sprockets. The original design had positioned drive wheels on the outside of the tracks, creating stability problems and exposing critical components to debris and damage. The revised configuration placed drive sprockets at the rear, protected within the track frame, dramatically improving reliability and reducing maintenance. This modification required redesigning the entire power transmission system, relocating the final drive, and strengthening the rear frame structure to handle concentrated loads, but the improvement was worth every engineering hour invested. Track design evolved rapidly as metallurgists and mechanical engineers collaborated to solve wear and breakage issues. The early simple flat plates gave way to pressed steel plates with integral cleats, heat-treated to Rockwell hardness values that resisted abrasion and deformation. Pin diameter increased from 1 inch to 1.5 inches, with upgraded steel alloys that could withstand fatigue cycling far better than the original materials. Track width increased from 4 feet to 5 feet on later models, further reducing ground pressure and improving flotation in soft soils. The bogie wheel assemblies received substantial redesign. The original rigid frame that supported the bogie wheels was replaced with a sprung system using heavy coil springs or leaf spring stacks, allowing individual bogies to rise and fall independently. This innovation transformed the crawler's ride quality and, more importantly, maintained more consistent track tension over uneven ground. The sprung bogies also reduced shock loading on the frame and final drive components, extending component life significantly. Later models added sealed bearings with grease fittings, replacing the original plain bearings that required daily oiling and failed frequently in dusty or muddy conditions. Steam engine development paralleled track improvements. The Holt 60 featured a larger boiler, 10 feet long and 42 inches in diameter, capable of maintaining 150 psi even under maximum load. The firebox was redesigned for more efficient combustion, with better air circulation and a larger grate area that allowed the firemen to maintain consistent heat with less frequent stoking. Superheater tubes, borrowed from locomotive practice, passed steam through the hottest part of the firebox after leaving the boiler, increasing its temperature and energy content without raising pressure, essentially getting more work from the same amount of fuel. Power increased substantially. The Holt 60 developed approximately 75 horsepower at the drawbar, a 50% improvement over the original crawler. This came from larger cylinders, now 12 inches bore by 15 inches stroke, better valve timing, and improved steam flow throughout the system. The transmission system was strengthened with larger gears, heavier chains, and reinforced final drive housings that could withstand the increased torque without catastrophic failure. Competition spurred innovation. The Holt brothers weren't alone in recognizing the crawler's potential. C.L. Best, formerly a Holt employee and later Benjamin Holt's chief competitor, developed his own crawler designs incorporating different track configurations and steering systems. In England, David Roberts and Hornsby & Sons experimented with chain track systems for agricultural use. This competitive pressure forced continuous improvement. Companies that rested on their laurels found their machines obsolete within 2 seasons. World War I loomed on the horizon, though few in California's agricultural community anticipated how profoundly it would impact crawler development. The British military, desperate for vehicles that could cross trenches and break through barbed wire, approached Holt in 1914 about adapting crawlers for combat use. The tank, though it wouldn't carry that name until later, was born directly from Holt's agricultural crawler technology. Military contracts brought capital for research, demand for increased production, and urgency that accelerated development beyond what agricultural markets alone would have driven. The peculiar trajectory of crawler technology took an unexpected turn in 1914 when Europe descended into mechanized slaughter. The Western Front's trenches, barbed wire, and artillery-cratered no-man's land created tactical problems that conventional military equipment couldn't solve. British and French commanders, watching infantry attacks disintegrate against machine gun fire and wire entanglements, desperately sought a vehicle that could cross trenches, crush wire, and deliver troops or supplies into forward positions while providing protection from small arms fire. British Lieutenant Colonel Ernest Swinton, witnessing Holt tractors demonstrated in England, recognized their potential. The crawler's ability to traverse soft ground and climb over obstacles wasn't just useful for agriculture, it was potentially revolutionary for warfare. Swinton convinced the British Admiralty's Land Ships Committee to investigate armored tracked vehicles, leading to contracts with Holt for crawler chassis and engines. By 1915, Holt was shipping crawlers to England, where British engineers armored them, mounted weapons, and created the first tanks, machines that would debut at the Battle of Flers Courcelette in September 1916 and fundamentally alter the nature of ground warfare. The military application transformed Holt Manufacturing Company virtually overnight. Production expanded from a few dozen crawlers annually to several hundred, then thousands. The factory in Stockton doubled in size, then doubled again. Employment soared from 500 workers to over 2,000. The workforce changed dramatically. Where experienced agricultural mechanics had dominated, now the factory trained farmhands, urban workers, and even women to manufacture crawler components on rapidly installed assembly lines. Quality control became critical. A track pin failure was an inconvenience on a farm, but could be fatal in combat. Military demands also pushed technical development in directions agricultural use never would have. The Army wanted crawlers that could maintain higher speeds, not the 2 miles per hour of field work, but 4 or even 5 miles per hour for tactical mobility. Engineers responded with more powerful engines, improved transmissions, and redesigned final drives that could handle sustained high-speed operation. The military wanted better hill climbing ability, resulting in lower gearing and more powerful drawbar pull. They wanted improved reliability under extreme conditions, driving advances in metallurgy, lubrication, and component design that would benefit agricultural crawlers for decades afterward. Perhaps most significantly, military use demonstrated the crawler's versatility beyond anyone's initial conception. Crawlers hauled artillery pieces across terrain that would have immobilized wheeled vehicles. They pulled supply sleds through mud that horses couldn't navigate. They powered winches for recovery operations, served as mobile power plants for electrical generation, and even operated as earth-moving equipment for fortification construction. This versatility wasn't lost on civilian observers. If crawlers could do all this in warfare, what else might they accomplish in peacetime? The war years also marked the beginning of gasoline engine adoption in crawlers. Steam engines, for all their proven reliability, were increasingly viewed as obsolete. Gasoline engines offered better power-to-weight ratios, faster startup times, reduced water requirements, and simpler operation. Holt experimented with gasoline-powered crawlers during the war, though steam remained dominant in agricultural applications until the early 1920s. The military contracts, however, provided capital for gasoline engine development that would have been difficult to justify based purely on agricultural sales. By 1918, Holt had produced approximately 10,000 crawlers for military applications, a staggering number considering that total agricultural production through 1914 had been perhaps 1,000 machines. Veterans returning from Europe had operated crawlers in combat, gaining familiarity with the technology and confidence in its capabilities. This created a post-war market of experienced operators who understood what crawlers could do and were eager to apply that knowledge in civilian contexts. The stage was set for the crawler to revolutionize construction, logging, road building, and mining in ways that would dwarf its agricultural impact. The 1920s brought transformation so profound that the steam crawler became a museum piece within a decade, not because it stopped working, but because better alternatives emerged. Rudolf Diesel's compression ignition engine, developed in Germany in the 1890s, had matured into a practical power source that offered advantages steam simply couldn't match. Diesel engines required no water except for cooling, eliminating the tender wagon and its constant resupply logistics. They could run on cheaper fuel, crude oil or kerosene rather than coal or wood. They started almost instantly compared to steam's 45-minute warm-up. Most compellingly, they were more efficient. A diesel might convert 35% of fuel energy into mechanical work, while steam engines rarely exceeded 15%. Holt introduced its first commercial diesel crawler, the Caterpillar Diesel 60, in 1931, a machine that represented the culmination of 27 years of tracked vehicle development. The diesel engine was a massive 4-cylinder unit displacing over 1,100 cubic inches, developing 75 horsepower at just 700 RPM. It weighed nearly 3,000 pounds and required 2 men to start, one manning the hand crank, later replaced by electric starters, another controlling fuel delivery. But once running, it was unstoppable. Smooth, powerful, and capable of operating continuously for 12-hour shifts with minimal maintenance. The transition wasn't immediate or smooth. Steam had fierce defenders, men who'd spent their careers mastering fire and water and weren't about to retrain on compression ratios and injector timing. Early diesels were finicky, particular about fuel quality, prone to hard starting in cold weather, and expensive to repair when internal components failed. But economics don't care about sentiment. A diesel crawler could be operated by a single man where steam required two. Fuel costs ran about 30% less per hour of operation. Maintenance intervals were longer and component life was better. Farm managers did the mathematics and ordered diesels. The last steam crawlers rolled off Holt's production line in 1934, though many continued operating into the 1940s. Some stubborn operators preferred steam's simplicity and forgiveness. You could fix a steam engine with basic tools and mechanical knowledge, while diesel repair required specialized training and equipment. A steam engine would run on almost any combustible fuel. Diesels demanded clean, specific petroleum distillates. But these advantages couldn't overcome diesel's fundamental superiority in almost every performance metric that mattered. Meanwhile, the crawler's application expanded into territory Benjamin Holt never imagined. Construction companies used crawlers to build the massive infrastructure projects of the New Deal era: dams, highways, aqueducts. Logging operations employed crawlers in terrain where wheeled vehicles and horses were useless. Mining companies adapted crawlers for ore hauling and earth moving. The technology that solved a farming problem in California's Delta became the foundation for the mechanization of earth moving itself. The merger of Holt Manufacturing with C.L. Best Tractor Company in 1925 created Caterpillar Tractor Company, consolidating crawler technology under one corporate entity and accelerating development through combined engineering resources. The famous Caterpillar yellow paint scheme appeared, creating brand recognition that persists nearly a century later. Product lines diversified: small crawlers for orchards and landscaping, massive machines for highway construction and mining, specialized military variants, crawler-mounted excavators and cranes. The tracked vehicle that started as a solution for soft delta soil became the foundation for an entire industry. Yet something was lost in this progress: the direct, visceral connection between operator and machine that characterized steam operation. An operator operated controls. A steam operator partnered with his machine, constantly sensing its condition through sound, vibration, and steam behavior. The fireman's role, that specialized skill developed over thousands of hours tending flame and water, disappeared entirely. Efficiency gained, experience lost, the eternal trade of technological advancement. Visit the Holt Museum in Stockton today, and you'll find a 1908 steam crawler preserved behind velvet ropes, its tracks frozen in mid-rotation, boiler cold for the first time in over a century. The machine radiates an aura of crude potency, 20 tons of iron and steel that represents the moment tracked vehicles transitioned from fantasy to reality. Children press their faces against the display barriers, perhaps sensing something profound even if they can't articulate it. This thing was genuinely new. Before it, tracks were experimental curiosities. After it, every tank, bulldozer, excavator, and tracked military vehicle shares its DNA. The numbers tell part of the story. From that first experimental machine in 1904 to the final steam crawler in 1934, Holt and its successors produced approximately 20,000 steam-powered tracked vehicles. These machines plowed millions of acres, constructed thousands of miles of roads, supported military operations in 2 world wars, and established manufacturing techniques and design principles still evident in modern tracked vehicles. Caterpillar Inc., the direct descendant of Holt Manufacturing, remains the world's largest construction equipment manufacturer, with annual revenues exceeding $50 billion, a corporate giant born from solving one California farmer's soft ground problem. But statistics don't capture the human dimension. The operators and firemen who mastered these machines, who risked boiler explosions and track failures and heat exhaustion to do work that had never been done before, built something beyond the physical. They proved that human ingenuity could overcome seemingly absolute limitations. Soft ground that had been an impassable barrier for millennia became merely another challenge, solved through mechanical cleverness and determination. This lesson, that impossible problems require only the right tool and sufficient will, echoes through every subsequent development in construction and agricultural machinery. The crawler's influence extends into surprising places. Tank warfare doctrine, from World War I through modern conflicts, rests on mobility advantages tracks provide over wheels. Moon rovers used tracked locomotion based on principles Holt pioneered. Modern agricultural GPS-guided tractors, autonomous mining equipment, and remotely operated construction machinery all descend from that first awkward crawler that Benjamin Holt drove across a Stockton test yard. The concept of distributing weight across articulated metal tracks, so revolutionary in 1904, is now so fundamental that we rarely consider its origins. There's melancholy in this success, though. The last men who operated steam crawlers professionally are gone now. Their skills and knowledge vanished except for what was documented by historians and museums. The particular expertise required to maintain 150 psi in a moving boiler while navigating a plow through delta peat is extinct, as surely as Stone Age flint knapping techniques. We've gained so much in efficiency and capability, but we've lost the direct, unmediated relationship between human skill and machine performance that characterized steam operation. Modern crawler operators work with air-conditioned cabs, computer controls, and diesel engines that start at the turn of a key, safer and more productive certainly, but perhaps missing something essential about the partnership between worker and tool. Walk through any construction site, watch tracked excavators carving foundations, bulldozers shaping earth, and recognize the inheritance. Every one is a descendant of Holt's crawler, separated by a century of refinement, but fundamentally the same in principle. They float on soft ground not through magic, but through the same elegant solution Holt discovered: spread the weight, multiply the contact area, create a machine that builds its own roadway as it moves. Simple in concept, revolutionary in execution, permanent in impact. Benjamin Holt died in 1920, living just long enough to see his crawler transform from agricultural oddity to indispensable tool. He witnessed its military application, its commercial success, and the beginning of its diversification beyond farming. What he couldn't have seen was the full extent of his legacy, that the machine he built to solve one problem would become the platform for fundamentally reshaping how humans modify their physical environment. Every highway cut through mountains, every dam impounding rivers, every strip mine extracting ore, all rely on descendants of his 20-ton crawler. The machine sitting in that Stockton museum is more than metal and engineering. It's a monument to a particular kind of American innovation. Practical, commercial, focused on solving real problems rather than pursuing theoretical elegance. Holt didn't set out to revolutionize warfare or construction. He wanted to plow delta fields without getting stuck. That the solution to his modest problem created ripples that spread across a century and around the world speaks to something profound about unintended consequences and the power of a genuinely good idea. So here's to the steam crawler, ungainly, dangerous, obsolete within decades, yet utterly transformative. Here's to Benjamin Holt, who looked at a stuck tractor and imagined something better. And here's to the nameless operators and firemen who mastered these iron beasts, who fed their fires and minded their water and learned to dance with 20 tons of moving steel. They built fields where swamps had been, roads where wilderness stood, and a technology that would shape the industrial world. Their monument isn't bronze or marble, it's every tracked vehicle that moves earth, every machine that conquers impossible ground,
every heir to the crawler that taught machines to walk.